Thank you very much for the introduction. My name is Bernhard Schranz. I'm a structural engineer by training as well. Did my PhD in structural engineering in Zurich at EMPA and ETH in the field of structural strengthening. And I'm responsible at Sika for market development for infrastructure, Europe North, Europe North, DACH, and Europe South, and also responsible for the product management of strengthening in the EMEA region. Just very, very briefly who we are. You might have heard of us as well. So we're a multinational company in several business fields. We're 33,000 colleagues now in about 100 countries. We're producing in 400 factories, and we're quite proud that we have about 108 patents each year. These are our business fields, and today we're gonna talk about what we call engineered refurbishment. So we're talking about reducing CO2 impact of the built environment. And why is this important, or why is this becoming more of a pressing issue? I'm sure everyone has their own answers for this as well, but here are some facts. So depending on the study that you read, most of them say something similar. About 20% of global CO2 emissions are caused actually by construction materials. And so we can track back 13% to the actual load-bearing structure. Most of the countries, including also big corporates or also small companies, have pledged to net zero by 2050. Then what makes everything more complicated is that 70%, when we talk about some of our biggest infrastructures, so bridges, 70% of those are already older than 50 years. And then so that we have a very old infrastructure, but on the other side, on the demand side, only when considering 2014, individual transport increased by 20%, public transport even by 51% in that time frame. So you can extrapolate that to now. And also transported goods increased by 14% since the 2000s. So the demand side or the load side is getting more and more challenging for these old infrastructures. And then we have market dynamics like raw material scarcity and also price fluctuations, which makes it hard to implement new solutions in the markets. And what I found a nice quote, you can request these sources later of these statements here. But what I found interesting is also most buildings we live in or we will use in 2050 that already exist today. So thinking about all of these things, a holistic life cycle approach is actually essential for fact-based decision making. And what we always have to do in construction, of course, link also costs to the emissions. And when we think about now, why is this especially important? Because considering this graph here, in the very, very early project phases, you can still influence your costs. But then when it comes to more concrete phases or even the use, then you're stuck with all the costs that your structure, let's say, produces every year. And you can't influence it enough. So an early long-term view is very important. So what are current strategies? Well, I've identified mainly three, which are increase the lifespan of structures to reduce the CO2 impact, which can be done, of course, including the carbon fiber products that you're about to see, protect the structure against environmental influence, what we call the Sika guard range, and effective repair material uses for all circumstances, we call monotop. Then using high performance materials at the right place instead of masses of low performance materials. They actually might have higher CO2 impact per kilogram, but when you check the whole structure and their effects of those materials, then you will find soon that this is very effective to reduce emissions. And this also includes high strength materials such as our ultra high performance concrete, the Sikacrete 920 UHP, it's called with us. There, This graph here I found very interesting. It was conducted during a study at EPFL in Lausanne in Switzerland. So you basically have here the global warming potential in kilogram CO2 equivalent, and here the service duration. This is a bridge deck repair, let's say. So you can, in the beginning, you can do the bridge deck repair with standard concrete in black, or let's look at the green line, the green dashed line with ultra high performance concrete. And you see they have a similar, or let's say the ultra high performance concrete has a higher CO2 impact in the beginning, but then every year when you have to replace the less performant material, the concrete, you increase the CO2 impact, and of course you can replace the y-axis here with cost as well, while the ultra high performance concrete stays virtually the same. So that means you might have higher CO2 impact maybe in the beginning, but and cost, but on the long-term view, you will have much lower of both. And then if you have to use a lot of material, then use low impact materials, of course. So CO2 reduced cementitious materials like we have in the monotop range, bio-based materials like the Sika guards, and low impact adhesives as well. So life cycle analysis in terms of cost and emissions is important, but how often is it really used at the moment? We conducted this study in Switzerland. We found that in terms of emissions, yeah means yes. So in 9% of all construction projects we investigated, life cycle emissions were actually investigated. And nicht bekannt means they didn't give an answer, but we are almost certain that this is also a no. So in most cases, they are not even looking at the emissions in a life cycle approach. When it comes to cost, it's a little bit higher the number, but also here you can add these 39% also to the no. It means only in a quarter of the construction projects, the life cycle costs were looked at. And then when you look at certification labels in terms of sustainability, most of the cases it's not done. So here these are local Swiss labels, but here you also have some international ones. You can insert whatever name you want, but in each country, it's probably not better than this graph, where in most cases there is no certification. Some more roadblocks that you encounter, of course, with aging infrastructure are the loads, as I said, are increasing. You have damaged and deteriorated materials. You have a change in use. You have oftentimes errors in calculations or execution, or you change the statical system. Like here, you want to remove this center support. And this all leads you to structural strengthening being essential for lifetime extension. So let's have a look at the solutions that are currently in the market. We believe carbon fiber is a highly effective solution. So what it is, basically carbon fibers embedded in an epoxy matrix, usually, which gives you carbon fiber reinforced polymer, so CFRP. When you compare the CFRP the carbon fibers to a hair, carbon fiber is much smaller. So in each CFRP plate, you have thousands of those fibers. Then you might know this material anyway from different industries like high performance sports, motorsports, or even the aviation industry. And we were among the first ones who brought this together with EMPA to the construction market. Material prices decreased, and with a lot of testing in the 80s, in the end led to the first products and the first site applications. So the very first one was in 1991 on the pre-stressed concrete bridge. I recently checked, and the strips are still there. And also 1992 on the historical timber bridge. So here you see still what our commercials back then looked like. And yes, why do we trust in carbon fiber? At the moment, or it's already widely adopted in all sorts of international standards. This is from the standardization side, which is a sign, of course, for wide adoption. So we then have very high tensile strengths. The material does not corrode, so it's highly durable. You can roll it up to lengths up to about 200 meters. You have, in the end, very small cross sections for strengthening. It's very lightweight, and it's also very simple. So if you compare, for instance, the equivalent steel to carbon fiber, it's several times smaller, let's say, if you make a strengthening with a carbon fiber solution. So when we go through the standard solutions that are there at the moment, so what you will usually use is CFRP plates that you have on a roll. This is fabricated in the factory, and you have all sorts of stiffnesses usually available and different cross sections as well, and you define those depending on the load and surface needs that you have. You can also, so usually you bond them externally, like you see here on that bridge, or you can also have them in a near surface mounted configuration, and you have a smaller cross section that you embed in a groove. What you can also do is pre-stress them. So in some cases with very high demands, you can also, or post-tension them, you can post-tension them and also increase serviceability considerably and also utilize the material even higher. And they're usually glued to the surface with an epoxy resin, which we call Sikadu 30. So here is yeah, it's not a very scientific test, but very nice to look at it. We had two concrete beams. One was unreinforced and one was reinforced with a carburetor strip. And then both beams were loaded. So this is the unreinforced beam. And as expected, the beam cracked and immediately failed. Then we tested the strengthened beam, and it did not only hold the first load, but also even more loads. And we had a lot of colleagues coming also from the offices to stand on the new beam. And it's not only static loading, but we had them do a little bit of sports, and also had them dynamically load this little beam. So it's a nice demonstration how the material increases the structural performance. Then next to the plates, we also of course have the fabrics, and the fabrics are usually the CFRP. The polymer, the reinforced polymer, is created on site. That means you take the fibers as a sheet, and then you apply them together with epoxy onto the structure, and then the CFRP is created. Material parameters are a little bit different. Also the stiffness, you will find all this info in the data sheet. And usually we have widths of 300 to 600 millimeters. And these are usually the roll lengths. We also have different fiber contents depending on the structural needs and on the loading. This is the epoxy that you need with this material. It's a little bit less filled or viscous, so that or higher viscosity, so it nicely penetrates through the mesh here. Up to 10 layers, depending on the structural applications, can be used. And of course, as you see here also, custom shapes are possible. This was a nice site example from Sweden. It was an old train repair shop, and this was near demolition, as you could imagine. And then the whole roof was strengthened with fabrics. So quite the effort, but in the end, they could maintain the structure. So you could imagine the CO2 impact that was avoided against the option that the whole building would have been new built. What else is there? So we also have prefabricated angles, which are post-installed anchors, stirrups, in case you have less shear capacity. And what we, of course, have been using for a long time is what we call the FX50. It's a carbon fiber strand that you can use for force transfer between certain all sorts of elements. So when you cannot have the rigidity of the angles or the plates or the fabrics, you can use this strand to create anchors, for instance, under the CFRP angles or under the fabrics to really put in the forces highly into the compressive zone or close the shear strengthening on top. As you can see here, this was actually a shear strengthening only out of this material. Some further applications, so standard shear strengthening, crossings of plates, very impressive applications on cooling towers and also chimneys. And this is also some applications that we have, since we're also active in the Middle East, this was a pipeline strengthening. So all sorts of applications are possible. So when we talk about lifetime extension, strengthening oftentimes can be the enabler of the lifetime extension. These are two nice examples. The first one is this was the K Tower in Sydney. So this was actually an old concrete building, a high-rise, where they actually wanted a new high-rise there. And they were able, by strengthening of the core, the concrete core, to build a new structure around it. So here you see the result, and it's actually it looks like a completely new building, but inside there is what really holds the building is a concrete core, which is from 1976 actually. So by doing that, we could save 12,000 tons of CO2, by preserving 95% of the core, and also, of course, save 85 million of construction cost. And as also in the next project here, the strengthening was really an enabler. So here we combined nicely the properties of the standard product, the carbo shear, which is this angle, and in combination with the FX50 to transfer the forces deep into the concrete, and the combination of both really made difference here. So really there was a lot of material that went into this, 1,600 pieces, and over 500 meters of these smaller elements to strengthen it. So to put also this a little bit in numbers, we conducted a study on various types of structures and wanted to see what the really the CO2 effects or the cost effects are on the entire lifetime. And here, if you compare complete demolition and rebuilding with refurbishment, we at first wanted to see where the actual costs come from. And as expected, when you look at the CO2, most of it, when you rebuild the structure, most of it comes from materials manufacturing, because there's a lot of material that goes into this, and some also materials disposal at the end of the lifetime. UBPs are everything else that is not CO2, so also waste and so on. And here the trend is similar. And when you go to refurbishment, it looks a bit different because you use a lot less material. And then you have the material disposal becomes more significant because you also dispose of the entire building at the end. And then the operational phase gets more important. And when we now look at total emissions and total cost, you see that rebuilding has much, much higher CO2 impact than refurbishment. And also what was interesting also in terms of cost, this was the refurbishment was the better option. Because most building owners, they actually assign, when you completely refurbish a building, like the city of Zurich, you can assign the initial lifetime to a totally refurbished building. And this is why refurbishment has a much nicer or much better cost footprint, let's say. And this is even without considering operational hindrance cost. It means when they have to demolish the complete parking garage and they don't have any revenue from that for years, in comparison to when you can, when you have an intelligent refurbishment concept and can keep some of the structure still in operation. This comes on top. So that means that the difference, the delta between those two will be much bigger. So then we thought, okay, how about our materials? Can they actually last so long? And we have, because we were involved from the beginning, we have about, we found very old projects where some of the materials were used. And here you see some road, let's say a road bridge, Oberried-Meiningen, between Austria and Switzerland, where it was strengthened actually in 1996. And last year, EMPA took some photos. Thank you very much to our colleague Safiris at EMPA. And the Carbudur really, or the CFRP really works, or this was based on visual inspection, of course. We're currently working on also finding out the real material properties. And then here you have the timber bridge seen from the beginning, which actually very, very old, much older than also 1900s. But it was strengthened in 1992, and here also the C4P strips really look great. Here is a more scientific approach. We did some tensile tests of about 30 years old material, and here really the deterioration of material properties, it really is lost in the scatter of the material. It means after almost 30 years, material properties in terms of tensile strength, Young's modulus, and ultimate strength virtually did not decrease at all. So what are the key takeaways from this? It is the pressure for lifetime extension is really increasing due to several factors, external factors. Life cycle approach is essential, but it's not widely adopted still. Refurbishment can really have lower cost and emissions than complete demolition and rebuilding. Decreasing maintenance cycles decrease emissions and cost, and this has to be checked which materials are really used there. Please use highly durable, high performance materials because it will have a big effect on the life cycle performance. Also use CO2 reduced materials if you have to use a lot of them. And of course, use C4P materials to enable sustainable lifetime extension. And with that, I would like to thank you very much for your attention and hand over to my colleague Antonino Montalbano. I think Senna will do the questions afterwards, or?
Yes, it's better at the end of all the presentations.
Oh, okay, thank you, Bernhard. I will take over. Just please confirm that you can see my screen.
Yes.
Yes.
Okay. So my name is Antonino Montalbano. I'm a structural engineer. I'm from Italy. And currently I'm in charge, I'm responsible for the structural strengthening solutions for the SIGA group. I will go very fast with the first slides because Bernhard already showed you something about and mentioned the SINS bridge. It is one of the first ever application in SICA, and I will go fast also on this because Bernhard showed what is our current product range that covers all the needs with several products and solutions to cover all the needs. I would add something related to some special applications that can be useful and can, let's say, help to find a suitable solution in some conditions where the classic FRP systems cannot be used. I'm referring to what, let's say, internationally is called FRCM systems or sometimes TRM systems. So basically, all the systems that Bernhard, the presentation before me, showed are FRP, where FRP stands for fiber reinforced polymer, and are composite systems that use as a matrix an organic matrix, normally epoxy based. So I will give you a quick overview on the FRCM, where, let's say, the concept is the same, so a composite material, but instead of using an organic matrix, in this case we use an inorganic matrix that can be cement or lime-based matrix. The systems are thicker than the classic FRP because we are talking about systems with a thickness that can go between 5 and 15 millimeters, and normally we use glass fiber or carbon fiber or sometimes basalt fibers with a spacing that is lower than 30 millimeters. So we use, let's say, dense grids. And the advantages of these systems is that we need less surface preparation in terms of smoothness of the surface. So we still need to have a clean, dust-free surface. But since we are using a slighter, thicker system, we can, let's say, have a less smooth surface and it will be okay. But one of the main advantages of this system is that using an inorganic matrix, these systems can be applicable on humid substrates. So in this case, the application normally, if you imagine a humid substrate, like when we work in a water tank or in a buried structure, when we have to deal with a humid substrate, the application of the classic FRP and the epoxy resin is still possible, but we need some special applications. So these systems are not a replacement and they don't go in direct competition with the classic FRP, but are systems that allow us to work in special application or service conditions. I want to focus my presentation introducing quickly one of our systems. It is called carbon or grid system. It's a FRCM system that uses a carbon fiber grid, biaxial balanced carbon fiber grid. And then we have two different possible cementitious matrix that can be used for the system. One is mainly used for concrete substrate, is the Montop 3200, and one is mainly used for the masonry substrates, that is the 3260 grid mortar. The grid is quite special, so it's a biaxial non-woven grid. So non-woven means that both the warp and the weft are plain without any weaving. The production system is patented and it's not a dry fiber, but the grid is impregnated with an acrylic-based resin, and this allows an excellent and improve dramatically the adhesion with the mortar. And thanks to this impregnation, the grid is stable, easy to handle, and to be applied. In the pictures on the bottom left of the slide, you can see, let's say, a weight on a grid. On the left, you can see the carbon or grid. On the right, you can see a classic carbon fiber grid with the dry fibers. So it's extremely, and we will see in an application that I will show shortly, how easy it is to handle and to embed the grid in the mortar. So the main fields of use are masonry or concrete in various structures, where having the possibility to work with humid substrate, this reduce the disruption time and allow us to work directly on the humid substrate. So the main use are in the wastewater, freshwater, and sewage structures, or in terms of infrastructures, they are typically used in cooling towers and chimneys. And I would add that can be used normally for masonry and heritage structures, where the use of the classic FRP is possible, but sometimes in this type of structures, we will see shortly an application, we need a diffused strengthening system that cover all the surface. So in this case, most of the time we prefer to use these FRCM systems instead of the classic FRP. This system, we have a lot of external test reports. Obviously, the mortars that we use are CE marked, and we have the international patent for the grid, as I mentioned. And for France, we have the local approval for the use as a structural system. We have the AVI technique issued by the CSTB. The system is fully tested. We perform tests on the grid. We perform tensile tests on the FRCM specimen, and we did some lap shear tests for the characterization of the adhesion on a standard substrate. The standard substrate can be concrete, like in the picture you can see on the right part of the slide, or the standard substrate could be bricks, tough, natural stones, for example. I'll quickly show you two references. One is on an heritage and historical buildings, and one is on, let's say, a water infrastructure. For the first one, this is, we are in Florence in Italy. You know that in Italy we have the main Renaissance museum in the world is the Uffizi Museum, and during the years we applied several strengthening systems on this structure that was built in the 15th century, so 600 years ago. In this case, apologies for the quality of the pictures, but these are screenshots from a video we did during the application. This is, if you go to Florence, this is the new entrance of the museum, where there is the ticket desks. And when they decided to change the destination of this room to the ticket desk, they needed to increase, let's say, the loads on these vaults. This is a big vault because the side is 10 meters, so it's 4 vaults combined with a column in the center on the lower floor. And in this case, we applied a glass fiber grid that we embedded in a inorganic matrix, and you can see the phase of application where the total thickness of the system is around 10-12 millimeters, and we embed this grid to strengthen and improve the load-bearing capacity of these vaults. These are another vaults also in the museum where we applied the same system on the vault, but additionally we applied, as you can see in this part, some glass fiber connectors to improve, let's say, the adhesion and the mechanical performance of the system in the sides of the vault. Just to go quickly to a completely different application, in this case, we fly from Florence to Paris, and in this case, we are in a sewage tunnel, and the request was to strengthen the sewage channel that had some problem in the top part with this crack that you can see in the right picture. And additionally, the request was a short disruption time of the channel, and just to increase the complexity of the work, you can see on the left picture this duct that were, let's say, some ducts where we had some fiber optics and cannot be removed or even moved. So the thickness that we had available for the application of the system was quite little. In this case, it's a humid substrate, so the application of the FRP was not possible, and even the roughness of the surface was not suitable for the application of the FRP, so we applied the Sika carbon grid system. So you can see the application of the first layer of the mortar, then the embedment of the carbon fiber grid, easy to handle. You can see that it's extremely easy to handle and to embed the grid in the first layer of the mortar, then fresh on fresh the application of the second layer of the mortar, and on the right side you can see the finish work, and we don't even need to wait for the full curing of the mortar, because as soon as the mortar is hardened, we can reopen, let's say, the channel in service and return to service. There are several other typical applications, but I will fly on it. I will just show you. We're talking about aqueducts. We are talking about water tanks in a wastewater treatment plants. We are talking about reservoir of drinking water and all these were reinforced and strengthened using the Carbotor grid. Just last 30 seconds to mention that we have developed and we, let's say, give to our customers a software. It's let's say 2 Excel spreadsheets, basically, one especially designed for masonry structures, one for concrete. With the masonry we can design shear in plane shear capacity of a masonry panel, or in plane of out of plane flexural behavior of a masonry panel, or a confinement of a column. With the concrete software, we can do shear of a rectangular T-shaped beam, flexural of a rectangular T-shaped beam, or a confinement of a concrete column. In this software followed the Italian design guideline CNR DT 215, and so this design is based on the Eurocode regarding the concrete and the masonry, and follow the Italian guidelines regarding the specific design of the FRCM systems. So this is a screenshot, let's say, of the software, and for me it's okay. I wait for your question, and I will be happy to answer question if you have it. So thank you very much.
Thank you very much, Antonino, for these interesting insights. I'd like to ask Professor Giovanni Terrasi to go ahead with his presentation.
Thank you very much. Hello, everybody from Dübendorf near Zurich. My name is Giovanni Terrasi. I am a mechanical engineer by training, but I then had a PhD with Professor Urs Meier here at IMPA back in the 1990s. So I was involved with externally bonded reinforcements on the basis of CFRP, I think I should say, from the very beginning. I am also teaching at ETH in Zurich at the Department for Mechanical Engineering at the University of Edinburgh at Structural Engineering, where I hold a course on mechanics of strengthening and repairing civil structures. My short case study focuses on pre-stressed, externally bonded Carbotor reinforcement of a fatigued structure, a welded steel box girder, a pendulum artwork in the hall of a quite well-known reinsurance company here in Zurich. That was the first slide. The next one would look at the box girder. It is a tapered 13 meters long welded steel 22 girder that is a quite low-grade mild steel with a yield strength in the range of 250 megapascal approximately. And here the original structure was carrying 2 oscillating TV monitors, each 80 kilograms in weight, and those monitors showing the share value of this company were oscillating here in the entrance hall of this reinsurance company with a period of oscillation of roughly 24 seconds, if I got it right. So this pendulum was doing something like 400,000 load cycles or oscillation cycles per year. So originally, the sections, which were built by welding steel plates, were butt welded one to the other. In the center here of the 13-meter pendulum, we have the electromechanical driving section, allowing the oscillation. The upper end has the equilibrating weight integrated in the tapered pendulum, while the lower weight is carrying the said TV monitors. The original design was a butt welding of the box girder sections, and on top they were screwed with each 12 HV screws. So a welding and screwing. But unfortunately, in the heat-affected zones of those welds, after 19 months of service, and this was back in the year 2003, we had dramatic fatigue cracks, which are shown on the next slide. So you see here the heat-affected zones, well known to be the fatigue, or the weak links, the weak areas in fatigue for a welded steel girder. Here we had dramatic cracks, and even the head of single screws were falling down in the entrance hole. Not really a good publicity for a reinsurance company, which then stopped the pendulum and asked EMPA for a refurbishment option. And here we teamed up with Carbolink. Carbolink is a former EMPA spin-off company, which was founded in the year 2000 by one of my PhD colleagues, Dr. Andreas Winisdorfer, together with Professor Usmaya. So we were asked here to propose strengthening solutions. Of course, non-invading strengthening solution, cost-effective, of course, with, say, an indiscernible impact. And we came up here with pre-stressed, externally bonded Carbodur CFRP protrusion plates, which, and this would be for the next slide, please, which were applied on the top and bottom flange, so tension and compression flange here over 6 meters, so anchored in lowly fatigue areas. And they were basically pre-tensioned and applied in a pre-stressed state to pre-compress the welded steel girder in order to shift here the bending stresses to pure compression at the level of the butt welds near the pivoting drive section. So we used 3 6-meter long pre-stressed CFRP laminates, 50 times 1 millimeter in cross section. So I would say that was a quite special Carbodur S510. We defined it in the short meeting we had before, pre-stressed to 900 megapascal, here to induce 45 kilonewton of pre-stress load per sheet, here bonded with an elastomer modified adhesive, an adhesive which is in use in the aircraft industry. It's used by Airbus, a 3M product, here to have a very ductile kind of adhesive on our steel. And in fact, after 20 years of monitoring, and we are monitoring here, my collaborators monitor this pendulum once a year, always in October. We inspect, we had no more fatigue cracks, no delaminations of the pre-stressed Carbodur reinforcements, and no pre-stress losses here measured with strain gauges applied and damage gauges here, in particular at the end of the laminates, to observe any relative displacements of the anchored zones, which in fact were not present. We're just measuring kind of temperature fluctuations caused by the difference in coefficient of thermal expansion of the CFRP and the steel. So this I should say is a very durable solution, and my last slide sums it up. So all pendulum welds in this case were renewed, and the tension compression flanges were strengthened by 3 pre-stressed CFRP sheets externally bonded and pre-stressed method here. No pre-stress gradient necessary here due to the high bond strength of the adhesive and the substrate for this particular case, and due to the fact that we are anchoring here far away from the fatigued area. And after 20 years of service and 8 million oscillations, our inspection showed that we had no fatigue cracks, no pre-stress losses, and no delamination. So we could increase here the fatigue life by a factor of at least 13. And that was my short talk. Thank you very much for your attention and for questions then in the question session.
Thank you very much, Professor Terrasi. And with that, I would like to hand over to Christian Vodrazka, CEO of BAP Consult in Austria, who will show us some very nice side projects. Let me share the presentation real quick.
I think you can hear me very well. Is this working?
Yes, perfect.
Okay. Thanks a lot, Bernhard, for your help.
No worries. Can you see the right screen?
Yep.
Perfect. Please,
Perfect.
stage is yours.
Thank you, Bernhard. Thanks all for the invitation to give a small presentation of what you call large-scale site projects. My name is Christian Vodrazka. I'm from BAP Consult GmbH in Austria. I'm the CEO. That's my company. And I'm working in this area for the strengthening systems, mostly of the time with carbon, for roughly 20 years now. And I would like to show you some main project I had done in the past and go over to the first project. Thanks, Bernhard. So this was a very nice project because it was a two-story design project. You see the first story, or you see the first floor. This was surrounded with 8 corner columns. And the goal was to demolish on the next slide. On the next slide, you see the demolition of the ceilings that you in the whole area, it would come to the point that this will be a whole area, or a hall in the future. This is means so 7.5 meters the height, and to connect the two columns together with the FRP section. Next slide, sorry. So this was the first thing. The first thing after the demolition of this, of course, we had this scaffolding to give the force inside that nothing is collapsing. Then we prepared the surface, of course. You see on the left picture, you see the primer, they're doing the primer work. Afterwards, they're doing the strengthening. The strengthening includes the carbon plates. We call it carbon plates, or we can say CFRP systems. And the last thing was wrapping around with the C sheets. You see on the left picture again, he's working very well because they are wrapping around. The work with the laminates are done. And on the right picture, you see the sprinkled surface. This is sprinkled. It is quartz sprinkled because after this work, they will protect with a fire protection render or fire protection mortar. This was the preparing. After the preparing of the wrapping and the strengthening, now it comes to the fact that it needs the fire protection system. This is the first thing was a mineral bonding layer. And of course, afterwards, we need also the metal and mortar, the metal inside. It calls a ripped expanded metal, call it. And the thickness of the mortar, because of the incline of the column, was up to 8 centimeters. And the last picture is, this was the finished product. It was a perfect surface. This was a mineral filler, was it? I think it was a gips basis. And so they have a really smoothy first surface because they all want to show them. They don't want to paint it. This was actually the last picture of the column. This was a 2-story design building with the construction of the FRB. It worked very well. It was done in 2024. And I visited this site, I think 2 or 3 times in 2024. And they're all very satisfied with this project. This is one project to combine 1 and 2 columns. So the next step was, I think, is one of the biggest one in Austria. It was a highway, or it was a street to the highway. You can see on the picture the apartment, and the static system was included the hollow core and ribbed slabs. This is actually my car, and this was on. It's not a river. It's a small what I can say, small water in Austria, a channel we can see, and on the side. The problem was we always use the forklift, or we need some Steiger, also heavy things to put up the laminates. Now you see it, now it's working. The carbon plates were applied on the beams, on the concrete beams. In the first step was on the concrete beams. Then you see, but it was not so easy to apply the laminates, because we used 3 forklifts. We need these forklifts to bring these laminates up to the height. The height was roughly 6-9 meters, 6 up to 9 meters. And on the right picture, you see afterwards we need as well a carbon sheet. A carbon sheet was wrapped around, but not anchored in fully. But this was enough because the height was 1.50 meters. And in 2024, this was exactly in February, we applied the carbon plates on the abutment. This was the last work we did for this main bridge in Austria. Now, another smaller one, but was also very interesting, because this was from the Austrian Railway. The problem was they have exactly a time schedule. They only can close the railway, and in this time we have to prepare everything, the surface, the application, the reinforcement. And I think it worked very well because it was overnight. And this was the time frame what we got. It was 8 hours. The static system was ribbed. Yeah, this was the beginning. Also, we used the CFRP, or the carbon plates, C-sheets, and maybe a little bit different to the FX50. I used the SEEK anchors. This is a carbon anchor for the C-sheet. This was work in progress. Now see, the laminates are, so the length was 10, 12 meters. The length was, we prepared it, sorry, can I go back? This was exactly 12 meters, 10, 12 meters, the length, the main part, and we prepared it on the street. This was quite very well. It did really worked very well because the summer was there, so not the spring was there, but it was very hot here. And so we applied this really in a small time. And now you see on the right side, you see after the application of the C-sheet, we applied immediately the carbon anchor. The carbon anchor with the loose fibers on it, they are working, and they will spread apart, and also glued on the C-sheet to get up the forces in the pressure zone. And on the left side, this is a typical device what we used when it comes to the point of the application of the laminates. This is an gluing system. Yeah. And this was the railway. This was the ribs that we applied under the railway. This was the finished look. This was also a big project in Austria, or directly in Vienna. It's the 9th district of Vienna. It was the Medical Campus Vienna. Was a really big project. It started. You see on the sides, you see Denkmalschutz. That means monumental protection. It's not so easy to work on that because you have really be careful with the demolition work, and of course also with the epoxy glue. The first step, what we did, was the diaphragma wall. The diaphragma wall was the first step we did. This was the diaphragma wall. You see on the right side the diaphragma. It was glued. It was not glued. Sorry, it was leveled. And afterwards, also after the leveling with a mortar, with a normal mortar, R4 system, R4 mortar, then we are preparing this vertically. This was for a technical reason. They needed this. And then we applied the carbon plates. Now you see the finished products. The carbon plates, I think it was 600 meters. Afterwards, 100 meter again, so 700 meter all in all. And maybe some interesting for you to look, it was the reference on the bottom picture. The reference was done on the mortar, because for this, you need 1.5 megapascal. This was the so-called the reference piece. This was the medical campus in Vienna, the first step. The second step was a little bit higher, because we had to reinforce as the static system means the rib slabs, and this was roughly 2 kilometers of that. You will now see from it was the fifth storage. It was the fifth storage. And you see now the rib slab, and the rib slab was made of, we need steel rebars or steel rebars, and then the laminates. The static reinforcement also includes the carbon plates or the CFRP system, and the shear force was done with steel shackle or steel stirrups. And you see there was a lot of them, and this is the whole picture. You see there was really big a quantity of the steel shackles or the steel stirrups. This was done in 2023, and nothing on there.
Yeah, that's it.
I think this was the, yeah. Okay. This was the last picture of the big projects. Most of the time I did this really well, because I visited all the sites. Took the photos, and I'm also a little bit designing this and helping the engineers to apply the laminates, and also for the workers to apply the laminates in the right, very well function. Thank you very much for this.